Welcome to Science Cafe on this snowy evening, which I think has cut into our crowd a bit. My name is Dave Brooks. I work for the Concord Monitor, write the Granite Geek column, and I recognize a lot of you. So raise your hand, anybody who has not been to a Science Cafe before. Okay, we have a couple of newbies there. That's about it, though. So, all right, excellent. Okay. Well, then I'll give you my spiel. Everybody else will have already heard it before. So this is Science Cafe. It was started almost about 7.5 years ago by a couple of science fans that had heard of these things operating in Europe, thought they were cool, wanted to bring them to New Hampshire, approached me to help them, got started. I thought it would fizzle out, but it has, as I said, gone for 7.5 years now. We operate one in Nashua as well. And frankly, inspired by us, there's several others. The Sea Science Center runs one in Manchester. There's one at one of the breweries in Portsmouth, Piscataqua, which is pretty much environmentally oriented. Somebody else has just started one. I haven't put it on the website yet. They just sent me a note. So there's at least 5 of them operating in New Hampshire right now, which is, I always say, we're the Science Cafe capital of the country. So the way it goes is we choose a topic, invite a couple of 2 or 3 knowledgeable people. You look pretty knowledgeable, and to sit and answer questions. And it is very much your questions. If you don't ask anything, we will just sit there in silence. Is this our third panelist?
Yes.
Excellent. Did you have a delightful drive here? Yeah.
It's a little slow.
Yeah. Sorry about that.
Nice to see you.
A couple things before I get started. So we meet here every month, the third Tuesday of the month, although we do not meet in December for obvious reasons. We'll be back in January. I think actually January is going to talk about genetic genealogy. If any of you have listened to the Bear Brook podcast about that cold case, which was solved partly because of genetic genealogy, we're going to be talking about that in January. But if you are not on our mailing list, there is a sign-up sheet there at the corner of that table. You leave your name written legibly and your email address written legibly, and we will send you the emails telling you when new science cafes are coming. One thing I always say is tip the staff well, because this is an annoying, frankly, venue for them, partly because they have to carry the schlep the food up and down the stairs. Also because there's a show across the street, which is why downstairs is so crowded. Usually we outnumber them greatly, but so that makes it even more difficult for them, so be generous. I always forget to say something, but whatever it is, it must not be that important. Okay, so we're going to go into it. I'm going to start out by asking each of the panelists to identify themselves and spend a couple minutes telling us why we should pay any attention to them whatsoever. And then I will ask the first question, and after that, it's up to you. I do not have an assistant, excuse me, so I'm the only person with a microphone. So raise your hand if you have a question, and wait for me to come with a microphone, because it needs to be picked up by TV. That's the other thing I forgot to say. ConcordTV films this and broadcasts it and also puts it online. So if you want to see yourself on television or on the internet, eventually you'll show up there. So if you have a question, wait until I come with the microphone, please. And with that in mind, why don't you pick up the microphone and start the introductions?
Hello, my name is Sarah Hopschwell. I am the Director of Education at the McAuliffe Shepard Discovery Center. Down the road, we are an Air and Space Museum.
A little bit closer.
A little bit closer? All right. We are an Air and Space Museum in honor of Krista McAuliffe and Alan Shepard, 2 New Hampshire space pioneers. They are certainly not the only ones, but we were founded in their memory and in their legacy. And so we provide programming as well as just a place to come and just learn about not only astronomy, but also aviation, earth and space sciences, the engineering of how we get into space. And I have been there for just about 18 months now, which is really exciting. I'm originally from Texas and then came up to New York for my grad school, and then started at the McAuliffe Shepard Discovery Center, and I've been enjoying New Hampshire and getting used to the snow. So I'll pass it off now.
Great. Hi, I'm Nathan Schwadron, and I'm a professor at the University of New Hampshire in physics. I do science on a number of different missions. I think right now I have instruments on 4 different missions. I also study radiation in space to understand, the effects for humans in space and for electronic equipment. And I've been in New Hampshire about 8 going on 9 years, and love it here.
Well, I think I win. I've been here since 1988. At least in New Hampshire, anyway. So I was at UNH for a while, and then I moved up to Dartmouth College, which is a long way from the ocean. Took some getting used to. So my name is Christina Lynch. I'm a professor at Dartmouth College in the Department of Physics and Astronomy. And a long time ago, I stopped telling people I do physics, because they go, ugh. And I tell people that I study the Northern Lights, because they say, oh, that's so cool. And that's just much nicer. But I do the physics of the Northern Lights. And so what my research group does in collaboration with institutes at Cornell and University of Alaska and a few other places is to build instrumentation and fly it through the Northern Lights. And in particular, what I'm interested in right now is trying to connect what we see in space to what imagery of the Northern Lights says, with the hope in the long run of being able to interpret the visible signatures in a more intelligent way. So.
I don't think I've ever had 3 panelists who actually limit themselves to 2 or 3 minutes. I mean, usually they ramble on and I have to cut them off. All right, excuse me. So I'll ask the first question. Now, this one is we've had kind of a vague topic, so we can go kind of anywhere. So I'm going to start with a really simple question that I jokingly put in my column, but it's actually a question that I've had asked and isn't perhaps entirely obvious, which is, how does a rocket actually fly in space when there's nothing to push against? And this was a serious question back in like the 30s and 40s when they weren't sure whether it would work, because there's nothing to push against. So why don't our educator will educate us?
So a lot of what happens to make sure that we can continue to fly in space is purely momentum. When we think back on the laws of momentum, an object in motion will stay in motion until acted upon by an outside force. And so most of the problem is getting it off the Earth, getting it through the atmosphere, getting it out of the orbit, and making sure that it is on the right path to keep going to where it needs to go. And in fact, most of the probes that we send out, that's where a lot and most of the fuel is used. And then if they've done all their math correctly, you're just adding just a little bit of thrust on one side or the other to do little manipulations to change your direction in space. But overall, most of it is just that momentum from that original launch. And then one of the big things to remember, of course, is there's not really brakes in space. You can't really push on the brakes. And so it's really just turning the thrusters in the opposite direction and therefore kind of moving you to slowly back up against it. And a lot of that is often when we're landing that we care about. But essentially most of getting us moving in space is done in the initial launch as opposed to in space. So that's the simple answer to that. I don't know if anyone else wanted to add to that, because I know both of you guys probably have some experience with this.
I just a simple concept that sometimes I use to get students to understand this is, has anybody fired a gun? What happens when you fire a gun? You feel a force come back at you, right? So basically what's happening in that gun, there's an explosion that goes off, and there's some stuff, the bullet, that goes out, and it goes out really, really fast. That momentum that's created to make that that has to come from somewhere. That comes from the gun. And so there's a push back against you in the gun. So in that case, imagine that you've got a rocket with a bunch of guns and a bunch of ammunition that's firing down. That's what ends up propelling the rocket forward. It's that momentum of the stuff that comes out of the back.
All right, so I've set a really low floor for questions, and everybody else's questions can be better than that, so.
This is a great topic, and thank you for coming. So, if I get this correctly, the thrust is through our atmosphere out into space. Are we going to build a platform in space to launch any spacecraft from? And if so, is there anything in the works currently to do that?
So this is a great question, because if most of the problem is getting it off Earth, then the logical answer to solve a lot of our problems is, well, can we launch from not on Earth? And so one of NASA's big plans for human space exploration is a multi-step process that we're at the beginning of, essentially, right now, which is with the end goal being getting to Mars by the end of the 2040s, about 20 years, which is crazy to think about, I think, for most of us. But to get there, what we want to do is, first of all, just redo a lot of this stuff. We have not sent people into space, I'll clarify that, except for going to the International Space Station. Does anyone know the last time we sent humans into space? Yeah, our Apollo missions. We have, besides the International Space Station, we have not sent people into space since the 70s. And so we have to almost relearn a lot of this information and test a lot of technology. And so the next step is to get people back on the moon first. The moon is about a 3-day trip from launch here on Earth. And so we want to get people back on the moon, test out different areas of our technology. The plan is to also have a manned lunar base on the surface of the moon, but then to also essentially have a station in orbit around the moon to test, again, just a lot of stuff. And then with the goal also of being able to launch from either the lunar surface or lunar orbit to go to Mars, which will cut out time as well as a lot of fuel to be able to launch from there, as opposed to here on Earth where we're dealing with a lot more atmosphere, we're dealing with more gravity, and so it will actually cut back on a lot of those concerns. So there is a plan in the works. I think right now the timeline is shifting, but I think right now the plan for those lunar bases as well as lunar stations above orbit are in about the 2030, probably 35 is I think what we're conservatively estimating right now. But I know both of you guys work with NASA a lot and might have more to say on that.
Well, I don't say much about people in space, but one of the platforms we're already using to launch things from is the space station. And so when they send cargo ships up there, a lot of times what they include are things called CubeSats that the students have built or that tech companies want to try out. And basically they throw it off the space station and it goes into orbit. And so in some sense we already have a platform in space to launch things from. It's a little low tech compared to sending people to Mars, but it's happening already.
So do they literally just sort of, toss them out the door? Obviously not quite, but I mean, is that all it takes to get it into orbit? It just automatically picks up the orbit of the ISS, or do they?
Right, well, it's in orbit if it's on the ISS, and so this is one of the mechanics questions that I use on my mechanics class exams, right? If you're on the space station and your laptop just stops working and you just can't stand it anymore and you just throw it at the ground, what happens to it? Right? And so it's going to a lower altitude orbit than you're in. So it starts going faster. And so you see it go down and scoot out in front of you. Whereas if you were to throw it up, it would slow down because a larger orbit is slower. And so you'd see it go up and fall behind you. Yeah. Angular momentum conservation. It worked for you.
Excellent. All right. Actually, I had a question here. I'll be back there in a minute.
This concerns EVA activity on Mars. Now, obviously, the spacesuit we used on the moon is inadequate because it was so heavy. Gravitation on the moon is 16.6 of Earth, and Mars is 38%. I do remember some series with Dr. Mike Massimino, former astronaut, looking at some designs for the EVA suits on Mars. Has any further progress been done in that area? Because obviously we're going to have that.
I don't know is an acceptable answer.
I don't know anything specifically. I would assume so. As you said, it is one of the crucial elements to having us live on Mars. We will be needing that suit anytime we step out of the habitat. I'm assuming we're going to have a habitat. I can't imagine we wouldn't have a habitat. And so I would assume they are constantly working on that. And I have seen potential plans for especially suits that would almost be assistive technology and essentially be supplemental to our strength or and to help us do tasks better on the Martian surface. But I do think those are a little bit further down the line. I think our goal right now is making sure, can we walk around, can we do science experiments, can we just travel on the surface of Mars, and again, not be weighed down by a massive suit. And so I don't know in detail is my answer, but I am positive they have people working on that, because as I said, that's a crucial part of living on Mars. Anyone else?
Okay. Elon Musk is going to have to wear something when he goes to Mars. We have a question way in the back here.
It looks like one of the limiting factors on human spaceflight is going to be radiation. What's the current status of thinking about what can be done about that?
Yeah, that's an area that's right in my specialty. It's something I've been studying. So one of the things that there's two parts to the radiation problem. One is the radiation that the sun spits at us, and so the sun is constantly bubbling up events that are called coronal mass ejections, and those create particles that get to very high energies, and that creates a radiation hazard coming from the sun to us. The other is coming from the galaxy, galactic cosmic rays, that are coming from outside our entire solar system and coming in. Whereas the events that come from the sun, they're episodic. They happen, every couple weeks or something like that. You see an event. What's coming from the galaxy is sort of ever-present background. Now, back in the Apollo era, which is the last time we were really going to the moon frequently, the sun and the space environment were very different than they are today. So if you look at the space environment right now, the sun does not produce as many events as it did back in the 1970s. And the galactic cosmic rays, as a result of the sun being less active, the galactic cosmic ray levels have gotten much higher. So overall, the galactic cosmic rays have much more energy, and as a result, that becomes an even more difficult problem in terms of radiation. So a lot of the progress in that problem has been, one, understanding the environment, understanding that this environment is changing. And the second thing, and this is really the piece that gets interesting, is understanding the biology. So how does radiation affect human beings? How does it cause damage? How does it damage cells? How does it damage the central nervous system, the skin, the eyes, bone marrow, etc.? And there's been tremendous progress in that area. We can't say that we have a solution, but I think we're starting to understand the solution space better. Right now, I think the best we can do with the radiation issue is to come up with feasible limits for the amount of time that we can expose people to that radiation environment and not have them get sick. And so that's, as we start to understand more and more about that problem, I think we'll be able to understand better how to protect, exactly what types of things to do to protect people. Just to give you one example, the central nervous system is something that we've learned very recently, is the subject that's very similar to head injuries in football. It's the damage that's done in small events that are occurring continually. And that's a big, big problem for radiation, because especially these galactic cosmic rays, you're constantly being bombarded by these events. So you're right, it's a very difficult problem. It's very thorny because there's not much we can do about it. And the best we're going to do is I think, continue to fly people with shielding and continue to make progress on the biological side and the environmental side.
Well, you're sending your experiments deliberately up into a high radiation area, aren't you? I mean, so what's the problem in terms of making equipment work or not work up there?
Well, I think it's a lot easier than an organic body that you don't really understand. You can always build in a redundant circuit if you know that you're subject to failure.
Is it an issue that has changed over your career? I mean, the early systems that went up there, they failed quickly because of radiation, or has it?
I think people know a lot better how to build electronics that are radiation tolerant. I don't think we've figured out how to build a person that's radiation tolerant, but you can build, fault correcting electronics that adjust for being damaged. So.
Cool. Yeah. All right. Okay. Was there somebody up here? That's it. Okay.
I don't know whether we've gotten our head of ourselves, but we've been talking about humans in space. You guys are already in space. You guys are already doing things in space. You're already doing experiments. My question is, I grew up as a kid who wanted to be an astronaut. I wanted to go into space. I didn't think that the wristwatch that Dick Tracy used would be the big thing. I thought we would be going into space. But my question is, what have humans being in space taught us that what you guys do hasn't taught us? And what are humans being in space likely to teach us that what you guys already do is likely not to teach us? Because I was, again, big proponent of humans in space from 11 years old, but it almost seems to me like what we've learned to do is keep humans alive in space and make Tang and Ovaltine and Velcro, but what about actually learning stuff?
I mean, you're preaching to the choir with me. I like it here. I like it here. I have no desire to go elsewhere. And I have learned huge amounts from the pictures that come back from Juno and the information that comes back from Solar Probe eventually. And, I think there's so much to learn about how our nearby universe works, or even our faraway universe works, just getting our sensors up out of the atmosphere and off the ground, that I'm happy doing that. But there is this, I think, visceral drive to get people elsewhere. And I think a drive like that is valuable, and you want to make use of it. But for my own work, I'm interested in how other planets work, and I feel like there's an awful lot to be learned by sending sensors out there without sending people out there. So, I mean, they both have roles. I don't know that I would say that sending people into space is in order to learn things. I think we learn stuff by sending our sensors into space. I think you send people into space for other reasons, which are equally valid and have other goals, but I don't know that learning things would be the primary reason.
If to be perfectly blunt about it, I don't think we've learned a lot about the cosmos from sending humans into space. We've learned a lot more by sending instruments into space. On the other hand, those of us that have to, try to continue to get money from Congress to get instruments in space, one of the things that you learn really early on is that a large part of the population doesn't care about what you learn in space. They care about, how many people you get on giant rockets. And, that sort of really, I think, is relatable to a huge part of the population. So there's a political side, a political dimension to this, where if we want to continue to motivate people to do science, we also have to come up with ways that they find it relatable. I mean, I'm sure you experience this at the Discovery Center, just how much that relates to a very broad cross-section of humanity. So in a way, I would say we've learned nothing, and in another way, I would say it's justified everything. So it's between nothing and everything, and you can choose the answer.
I completely agree with that. I don't have the experience of personally sending my objects into space, but based off of what we do, I completely agree. I think the human portion of it is to truly keep that drive going, to keep people interested in space. We have a lot of people who don't think space should be a point of concern right now. And I think, therefore, that getting humans into space does help keep people excited about space, which is very important. And I mean, I completely agree on the fact that, I mean, you look at Hubble Space Telescope, you look at James Webb in the works, you look at Kepler, which we just lost 2 weeks ago now. And I mean, those are where we are learning about the cosmos. But I will say there have been discoveries that do help us here on Earth, and that's through the fact of getting people to space, but also the experiments being done on the International Space Station, because there are people up there where we can learn what happens to the body when it is exposed to radiation. We are doing, I know, cancer research up on the International Space Station. So there are definitely aspects of of learning how to physically get people to space and to have them live in space that has helped us on a daily basis here on Earth and helped us learn more about our physical human bodies. But it is, when you're looking at truly understanding astronomy, truly understanding the cosmos, it is done by robots. But it is a valid question. We always have to ask, is it worth the risk to put people up there? What are we gaining from this? And so I do think it comes back a lot to just that drive to keep the research going, but also to try and understand us a little better.